Hey everyone, I wanted to continue on with the notes from our last class, and hopefully we can get this all in one video. We'll see how it goes here, but we're going to next talk about extended functions. The last little bit that was on here I didn't talk about in class, but these are just properties of continuity. Basically, the idea is if you have two functions that are continuous, then you can add them, divide them, multiply them, subtract them, multiply by some constant value, and you're still going to have something that's continuous. Okay, so that's the premise behind that. But I want to talk about extended functions. An extended function is a function that is obtained after a discontinuity is removed, right? So we said we can remove a discontinuity right when there's a hole. And this is what I was talking about last time, where we said we could rewrite the function so that it's not we could just write it a different way. Okay, so what we're going to do first is, and again, when you see a function like this, when you have a polynomial in the numerator and a binomial in the denominator, you're going to want to start by factoring it to see kind of what you can do with that. So the first thing I want to do is go ahead and factor this, right? So if I factor the top, I end up with x minus 5 and x minus 1 over x minus 1. Okay, so clearly I can cancel the x minus 1 factors, and that means that there would be a hole at 1, right? Because normally there would have been a vertical asymptote at 1, but because I can cancel the factors, that now gives me a hole at 1. So if I cancel those, I end up with this idea of x minus 5. And so then what I want to do is just plug in that value of where that hole is for x, right? So if I plug in 1 minus 5, that's going to give me negative 4, which tells me that my hole would be at 1, negative 4. And so what I can do then is write this as a piecewise function, which then removes that discontinuity from the function itself. Okay, and what I do by that is I'm going to call it something else. I'm going to call it g of x instead, because it's now a new function. And I'm writing it as a piecewise function. So my function is then x squared minus 6x plus 5 over x minus 1. And my other function is just going to be a constant. It's going to be negative 4. And so now all I'm doing is saying, okay, well, I will use the top when x doesn't equal 1, because then I can actually calculate it. But when it does equal 1, I'm just going to say it's actually equal to negative 4. And what that does is it takes where there was a hole, and now there is no hole, because when x is 1, you're filling in a value of negative 4. Okay, so we took a function that had a hole and we removed it by turning it into a piecewise function. And the way that we did that was we found the coordinates of the hole and then just used that to create the second part of our piecewise function. So let that sit for a minute. Replay that part of the video again. I'm going to do a second example, same idea as this first one. Okay, again, I have this polynomial over a binomial. So the first thing I'm going to do is factor. When I factor the numerator, I end up with x minus 6 times x plus 3 over x plus 3. And so if I cancel my common factors, that leaves me with x minus 6. But that tells me that I'm going to have a hole at negative 3. And so what I want to do is I want to find that y coordinate of that hole. And all I need to do is plug negative 3 into here. So negative 3 minus 6 is going to give me negative 9. And that's the y coordinate of my hole. From here then, I can write this as a piecewise function, which then takes my original function everywhere except, so x can be anything, it just can't be negative 3. Because when it's negative 3, the function value is going to be -9. So in essence, I have removed the hole, and now I've plugged, in quotations, I've plugged the hole by putting in this value of -9. So when x is -3, y is going to be -9, and I now have filled in that hole. So that's called extending a function, or removing that whole discontinuity. Okay, so that's a little bit on extended functions. The next thing I want to talk about is the idea of the intermediate value theorem. Sounds like it should be really complicated, but it's really not. Okay, so the intermediate value theorem, before we get into it, let's talk about this. If you're on a roller coaster, you're up here at W, do you agree that the only way to safely get to point Z is to pass through points X and Y? Right? My little car has to go down the track and pass through X and Y, doesn't it, to get to Z? You do. So for the car to go from point W to point Z, it has to go through X and Y because it has to stay on the track, right? In order for it to stay on in order for it to be safe, it has to stay on the track. I can't just skip, right? If you think of the Chicken Cross Road, I can't just skip over it. I have to actually cross it. Okay? That is, in just basic, like not even mathematical terms, that's what the intermediate value theorem says. IVT for short, we call it. Okay? And it basically says this. If you have this closed interval, meaning you have a starting point and an ending point, okay? Just like we did here, we had a starting point of W and an ending point of Z. Okay, so if you have a starting point and an ending point, that gives you a closed interval, then the function is going to take on every value within that interval. Okay, that's what this is all saying. Okay, it sounds really convoluted, but this is what it's saying. If you look at this graph, and it's a little bit hard to see on my paper, hopefully it's a little easier to see on yours. Here is my function right here. I'm going to try to trace it here. So here's my function. Okay. Here is my A value right here. Here's A. I think that was A. Yep, this is C right here, and here's B. Okay, so here's A, here's B. The intermediate value theorem says this. If this value is between A and B, what that means is that function value f of C is going to be between f of A and f of B. Okay, that's what it means. So, if I had a function, we're going to go with something very, very basic. Okay, if I had this function, here's my graph, and I have this function, we're just going to have this line. And let's say the equation of this line is 2x minus 1. And I'm only looking at it from -1 up to 3. Okay? If C is equal to 2, so my function f of x is equal to 2x minus 1. And I want to look at it on the interval from -1 to 3. Well, f of -1, I know I can plug in -1 for x, right? If I plug in -1, that would give me a total of -3. If I plug in 3, I would get 2 times 3 minus 1, so that would give me 6 minus 1, or 5. Okay, so whatever x, or whatever value I choose for x, that's between -1 and 3, the output I get, or the y value, has to fall between -3 and 5. The intermediate value theorem guarantees that. Okay, so let's say I had 2 for x, or let's say I had 0 for x. If I plug 0 in here, this function is going to be equal to -1. -1 falls between -3 and 5. Okay, so as long as I choose a value that's between -1 and 3, my output is guaranteed to be between -3 and 5. That's what the intermediate value theorem says. Okay, that only works if your function is continuous. So the necessary requirements is the function is continuous over a closed interval. So K, if you're looking at these letters up here, K is your output. That's what's on your y-axis. C is your input. That's what's on your x-axis. Okay, so if we look at this next example, it says, consider the function below and answer the questions. Is f continuous? Here's A, here's B. Is f continuous between A and B? Yes, it is, right? It's just one nice, smooth, continuous graph. Does K fall between f of A and f of B? Yes, it does, right? It's right here. It's between those two. So in this example, if C is between A and B, how many C's are there such that f of C is equal to K? So where is my graph crossing this dotted line? Well, it crosses it here, it crosses it here, and it crosses it here. So we could call that C1, we could call this C2, and we could call this C3. So there are 3 of them, and we just labeled them C1, C2, and C3. That's what the intermediate value theorem says. As long as you have a C value between A and B, you are guaranteed an output value between f of A and f of B, or between those two outputs. If your input is between your two inputs, your output has to be between those two outputs. That's what the intermediate value theorem says. Okay, so that's all in this video. I will finish up the notes with that last problem in the next video. Thanks, everyone.